In this video, we'll use Identify Debugger to capture a trace of components in the fabric from the Icicle Kit reference design. To begin, open a copy of the Icicle Kit reference design and ensure that the synthesize step has been completed. Once this is done, right-click on Synthesize and select Open Interactively to open Simplify. Once Simplify has opened, we need to create a new Identify implementation. To do this, select the synthesis implementation that already exists, right-click, and select New Identify Implementation. This will open up a new implementation window for you. Let's call this implementation Identify Debug, and then select OK. Once the implementation has been created, right-click on it and select Identify Instrumenter. And if you're prompted to save the project, click OK. When the instrumenter opens, you've got a control panel on the left-hand side to configure your instances. You've got a module browser in the middle to show you the modules in your design, and then an RTL browser on the right-hand side to let you select signals to be instrumented. For this example, let's try and capture some data moving through the fabric. So, for example, using Identify, we could capture data being written into this large SRAM from the MSS. If we had, for example, knowledge that the data in the SRAM was incorrect by reading it back and not getting the correct data, we might want to check where the incorrect data is coming from, and whether the MSS is writing incorrect data or whether the data is being corrupted moving through the fabric. So we can capture data from this interface here to the SRAM from the FIX0 core here, which is an AXI interconnect, and we can also capture the path from FIX0 into the MSS to see data moving from the MSS to the AXI interconnect, and then from the AXI interconnect all the way over to our MSS LSRAM here. Let's start off looking at the interconnect to the SRAM. We can see the SRAM instance here, and when we select it, its signals show up in the RTL browser on the right. We need to provide a sample clock, and if you click on a clock, an option list will appear and you can select it as the sample clock. We want to sample and trigger on the AOR address signal, along with sampling and triggering on the AW address signal. This allows us to capture a trace when a certain value appears on that signal. We could trigger only and we would not get any data for this signal, or we could sample only and only capture information. Now, to capture some data, let's sample the write data signal and also sample the read data signal. Now, if we have a look at the control panel, we can see that we have 128 sample only bits, 0 trigger bits, and 64 sample and trigger bits. And we can also see the clock source for this capture instance. If you click on the Edit ICE option, you'll be given options to reconfigure this implementation, such as enabling data compression, which we want to do here, and also setting a sample depth, which we can update to 512. If we have a look back at Libro, what we've now done is added a capture of data moving from this interface to this interface here. So let's go back and add a capture of data moving from this interface on the MSS to the interface on the interconnect. We can do this by adding a second ICE instance and using the Add ICE option. We can give this a name, so let's call this one MSS to AXI interconnect. Let's configure this ICE in the same way as the previous, with a depth of 512 and data compression enabled, and then click OK. Now we can see we don't have a sample clock or any sample, trigger, or sample and trigger bits. So for this instance, let's select FIX0 and we'll use the A clock signal as the sample clock. And then we'll select the same signals as we did before. So in this case, for the FIX0 we have this AXI master 0 input. So we want to select the address and data signals that are prefixed with master 0. So let's add the read address as a sample and trigger signal, the write address as a sample and trigger signal, and we'll sample the read data and the write data as well. And now, if we have a look in the control panel on the left, we can see that we've 128 sample-only bits and 76 sample and trigger bits. And we can change between the different instances available using the drop-down menu here. And we can see that we have a different number of sample and trigger bits between the different instances. So now let's save this identify implementation and close the identify instrumenter. If we return to simplify, we have our identify debug implementation and none of the synthesis steps have been run. So let's run synthesis now. Now that synthesis is completed, we can close simplify, and when we return to Libro, it's importing the netlist for our synthesized design. So let's give it a second to finish up. Now that that's complete, if we go to the reports view and into the resources utilization report, we can see that this identify core has now shown up in the resources. And if we expand it, we can see our two identify implementations shown here. So this is the capture logic that's been added into our design to allow us to capture a trace. All we need to do now is generate a bitstream and program the device. And we can do this by double-clicking Run Program Action from the design flow. Now that the device has been programmed, we can launch the Identify Debugger by double-clicking Identify Debug Design from the Debug Design section of the design flow. And when Identify launches, we can see the different implementations that are available up at the top here. We can select different modules that have been instrumented and also view the signals that we've instrumented. So for the MSS to AXI interconnect, there are no SRAM signals, but we have added trigger signals on the FIX0 interfaces. And if we change into the other implementation that's available, we've no sampled signals for FIX0, but we do have sampled signals for the MSS large SRAM. Now let's set up a trigger on the write address. Right click on it, and in the triggering menu, you can see the different options available. We can trigger when the signal's low or high, we can ignore the trigger, we can trigger on a transition from 0 to 1 or 1 to 0, or set a custom trigger, and let's select this now. For this example, we'll use a level sensitive trigger, and that's the first trigger option described here. We only need to provide a value that will cause the trigger to occur. So let's use a hex value, and we can do this by taking out the B and the X and adding in H and then 0x. So we're going to write to 61 million hex to test the MSS large SRAM. And we can double check this address from Libro by opening up the design and selecting the memory map view. If we expand all the tabs, we can see the MSS large SRAM shown here underneath FIX0, and its address is 61 million hex. So let's return to Identify, and we confirm that this address is correct, so let's select OK. And we can see this trigger is enabled. And let's set a trigger in the MSS to AXI interconnect on the write address as well, using the same address as we did before, which is 61 million hex. You can also set the trigger position in the sample buffer. So let's set this at the start of the sample buffer now. If you select the drop-down icon beside the run icon, you can select what instances you would like to run, or if you would like to run all instances. And let's run them all now. You can see the current status of Identify at the bottom, and at the moment it's just enabling the individual capture instances. So now we can see that Identify is running, and it's configured both of our capture instances. So now let's test it out and cause the trigger. To do this, we've got a Linux image open here, and if we log in with root, We can use the devmem2 tool to write to the MSS large SRAM. So if we enter devmem2 followed by 0x61million, which is the address of the MSS large SRAM, and then let's write a long, which is an L, and then we provide the data we'd like to write. So let's write 8 Fs followed by 8 zeros into the SRAM and see what happens. So now we can see that the write has occurred, and pretty much straight away Identify reacted to say it was downloading the samples that we captured. So now we've two waveforms that have opened up. If we expand this one and select all of the signals and set their data format to hex, this is the ICE waveform for the original capture unit setup. There's a second waveform here for the MSS to AXI interconnect instance, and let's set the data format to hex for that as well, and expand all the waves. If we put these side by side, we can see the ICE VCD on the left showing the address and the data moving into the MSS large SRAM, with the right address and the right data both being captured in this case. So if we had bad data going into the SRAM or bad address, we'd be able to see the incorrect values showing up here. And then as well, for the MSS to AXI interconnect, we also have the address and data showing up in this waveform. So if they were incorrect at this part of the transaction, we'd also be able to see it in this waveform. So this trace here for the MSS to AXI interconnect, if we go back to the Libro design, is showing us data moving from the MSS here into this fix0 AXI interconnect component. And if we have a look at the original ICE VCD, that is showing us data moving from the fix0 fabric component all the way over to the fabric MSS large SRAM component. So this has been a brief introduction to the Identify debugger, and we can use it to capture any signals we want within our RTL and generate a trace of them.